Alright, this is the extra practice for week 2. I'm posting it this way just in case you need to see how the problems were done. I'm going to have this posted as just a PDF. You can download the answers, but if you need to see the solutions, then you're watching this video. Alright, so the first one we're looking at the limit as x goes to -1 for this function. And notice that -1 does not cause division by 0 here. So because of that, I can just stick a -1 in here everywhere that I see an x. So I get a -1 up top, I get a -1 down below. -3 plus 2 is -1, and then a -1 divided by -1 is +1. Alright, 2, I'm taking the limit as x approaches 0 of this thing. 1 plus x, the square root of that, minus 1, all over x. Okay. Now, what we're going to do here, if I plug in 0 here, I get the square root of 1 minus 1, which is 0 up top. And then obviously if I plug in 0 here, I get 0 over 0. And that's what we call an indeterminate form. We can't say that it doesn't exist because the denominator is 0, and we can't just directly plug it in. So what we're going to do is we're going to multiply top and bottom by the conjugate of this numerator, meaning we're going to multiply top and bottom by square root of 1 plus x plus 1. Alright, square root of 1 plus x plus 1. Top and bottom. Okay, so this is equivalent to 1, so we're not changing anything. So what we get here, we get the limit as x approaches 0 of up top, this times this is just going to be 1 plus x. Like the square root of 9 is 3 times the square root of 9 is 3, and then 3 times 3 is 9. So it's kind of like we just remove the square roots there. Alright, then outside we get one of these. Inside we get a -1 of these. So they're going to wipe each other out, and then the last thing we get is the square root, 1 times a -1 equals a -1. Alright, that's up top. On the bottom, we're just going to keep it like this for now. Okay, now this 1 and -1 wipe each other out, and we get the limit as x approaches 0 of x over x times square root of 1 plus x plus 1. And now this x and this x wipe each other out, and we're left with the limit as x approaches 0 of 1 over the square root of 1 plus x plus 1. Alright, now notice that if I plug in a 0 in here now, I don't get division by 0 on the bottom. And since we don't get division by 0, we just plug it in, we get 1. The square root of 1 plus 1, which is 2, so we get a limit of 1/2. Alright, now also notice that if you didn't think to do this, I didn't tell you how to evaluate your limit. I didn't say you had to do it by hand. You could also have just plugged this into your y1 equation. The parentheses is needed up top because we got this subtraction, but we've got the square root of 1 plus x minus 1. Alright, I'm doing the original expression divided by x. Go to your table set. Alright, tell the table to start at the trouble spot, alright, the place that we're evaluating the limit, and tell your delta table to be something relatively small. And then look at your table, and you can see that we are approaching 1/2 on the left and right. So you could have done this with your table as well, but this is the way we would have done it by hand. Anytime that you see radicals involved, top or bottom, usually if you want the division by 0 to go away, if this limit does exist, then you're going to multiply top and bottom by the conjugate of the part that has the radical. Alright, number 3, I've got a graph here. I'm going to draw it real quick. Alright, and we're looking for the limit as x approaches infinity for this function, and we're also looking at the limit as x approaches negative infinity for this function. Alright, so the limit as x approaches infinity is as I'm going towards the right end of this graph. Alright, that's when I'm approaching positive infinity. Alright, the values as I start making my way into this region, we can see that y values, or the f of x values, are getting higher and higher and higher and higher and higher. Okay, so as I'm approaching the right side of the graph, or positive infinity, f of x is headed towards positive infinity. But as I make my way to the left side of the graph, negative infinity down here, as I make my way this way, the function is getting closer and closer and closer and closer and closer to negative 2. So as I make my way to the left side of the graph, the outputs are getting closer to negative 2. Alright, we want to find the limit as x approaches negative 2 of 1 over x plus 2. Okay, and this is one where I plug in negative 2. If I multiply top and bottom by the conjugate, I'll never be able to get rid of this division by 0. Okay, so this one's going to not exist, right, because it's a vertical asymptote at negative 2. We can't factor and remove this division by 0, so it doesn't exist. But if the top had been something like x squared minus 4, and we could have factored and canceled out the x plus 2, then that's what we call a removable discontinuity, and then we would have been able to evaluate it. But when you can't factor and can't get rid of this division by 0, plugging in that thing is going to give you division by 0, so it's not going to exist. You're not going to be able to get rid of it. Alright, this one is a little bit different from the last one in that it's a left-sided limit, or a one-sided limit. Okay, so we're moving in from the left. So if we pick numbers, if I plug in here 1 over x plus 3, and I go to my table, alright, the problem number here is negative 3. So if I make my table start at negative 3, and again keep my delta table relatively small, and go to my table, think about it. If we are approaching negative 3 from the left, think about how the number line works. Alright, here's negative 3, here's negative 2, here's negative 4. If we're approaching from the left, then we're talking about numbers like negative 3.1, negative 3.01, that kind of thing. So we need to be on this side of the table. Okay. Now notice, as we get closer and closer and closer to negative 3, the numbers are becoming more and more and more and more negative. Alright, negative 1,000. Okay, as we come from the other side, they're getting bigger, but positive numbers. So for number 5, again, this is a division by 0 we can't factor and get rid of, so it's going to be positive or negative infinity. And as we come from the left, we're getting negative infinity. Okay, another way you could figure that out is just looking at a graph of it. So looking at the graph, there's our problem spot at negative 3. As I come in from the left, it's going downhill. Alright, so we could also look at it from a graph and get it that way. Alright, for number 6, the limit as x approaches 7 from the right on 1 over x minus 7 squared. Alright, now this time, as I come in from the right, the numbers are bigger than 7, so like 7.1, 7.001, all that. But because I'm squaring it, it really wouldn't matter. If we're coming in from the left or right in an asymptote, one side goes down towards negative infinity, one side goes up towards positive infinity. But because we're squaring it, we're never going to be able to get a negative out of this. So it's going to head off towards positive infinity. Alright, again, you could use your graph feature like we did last time, or a table, and you'll see that it heads towards positive infinity, just like we did number 5. Alright, so now we're doing the tangent functions, or the trig functions. So we're looking at the limit as x approaches pi over 2 from the right in the tangent. Alright, couple of things you got to remember here. One, what the tangent graph looks like. So it has this look to us, and this is what we're doing. We're coming in from above pi over 2. So the graph is going down again towards negative infinity. The closer and closer and closer I get to pi over 2, the graph goes down further and further and further. Okay, so in this case we got a limit of negative infinity. Oops, 8. Alright, 8, we've got the limit as x approaches negative pi over 2, this time from the left. And we're looking at the secant function. Alright, now, secant is the reciprocal of cosine. Alright, so the cosine graph is symmetric at the y-axis. And remember, cosine starts off at its highest point, and then it dips down, and anyway, it makes a whole U-shaped looking graph from 0 to 2 pi. So at pi, it's at its lowest. It's down here at -1. Okay, if you recall what this is the graph of the cosine. I know we're doing secant, but we need cosine to remember how to do its graph. Alright, and then there's negative pi over 2. Okay, now we make the asymptotes at the zeros because that's where we divide by 0. Because remember, cosine is the reciprocal. So the secant looks like this if we reflect the graph of this cosine at those high and low points, and asymptotes at the zeros of the cosine, then we get the secant function. Okay, so this time we're coming in negative pi over 2. Here's negative pi over 2. Alright, and we're coming in from the left. So we're coming in this way. So as we, again, we're doing this, it's like this black line's not even there. So as we come in from the left, how do I get to the red curve? The red curve is the secant. I go down towards negative infinity. Alright, so as we approach negative pi over 2 from the left in the secant function, we get negative infinity. Alright, number 9, we want to find the vertical asymptotes of this function. So remember, to find vertical asymptotes, we factor and cancel out anything that can cancel. I'm going to pull this out of here, so it's x squared minus 16, so you'll see it is a difference of squares. On the bottom, this will factor as well. We need two numbers that multiply to 4 and add to 5, so 4 and 1. Okay, and then up top, I get a negative x plus 4, x minus 4, that negative on the outside. Alright, the 4's cancel. Oops. X plus 4's cancel. And then the only thing that's left is a negative x minus 4 up top and an x plus 1 on the bottom. Okay, now since this x plus 4 was removed via this cancellation right here after I factored, that means what makes this part 0 is the only vertical asymptote. So the only vertical asymptote occurs when x is equal to negative 1. Alright, 10. Find all points of the function where it's discontinuous. So we've got that absolute value shape, and then we got a hole right here, and then a closed dot, and a horizontal line. Okay, this is on the x-axis. There's our y-axis. Alright, and then this is at positive 1. Okay, so find all points where the function is discontinuous. It's discontinuous when x is equal to 1. Alright, just looking at the graph, that's where the gap is. Alright, same idea on 11. You got a graph that looks like this. On both sides of the y-axis, we head towards positive infinities. We make our way to 0, and then we have holes here and here at negative 2 and positive 2. Alright, so here, oops, there should be 1. Here the discontinuities take place when x is positive and negative 2, and then at 0. Alright, 12. Is f continuous at 1? I've got the graph. And remember, to be continuous, the three things have to happen. Alright, f to be continuous at x equals a. F of a must exist. Alright, that works. The limit as x approaches a of the function must exist. Alright, that's also true here. And then the third thing that has to happen is the limit as x approaches a of f of x must equal f of a. Alright, and that's where we don't have that happen here. We have a closed dot at 1, negative 2, and the open dot occurs at 1, 4. So because of that third thing, it's not continuous at x equals 1. Alright, same idea on 13, except on 13 all three things are good. Alright, 13, at x equals 0, the limit as we approach from the left and right does exist. There's a closed dot there, so the limit does equal the output. So yes, f of x is continuous. When x is equal to 0. Alright, 14. We want to know all the intervals where a function is continuous. Now, there was something in our notes that said any rational function, and that's what we have here. This is a rational function, meaning a polynomial divided by a polynomial. Any rational function is continuous everywhere that it's defined, basically on its entire domain. So, if we factor that bottom, alright, we need two numbers that add to this, multiply to this. So that's going to be negative 8 and negative 5. These are the two places where this thing's not defined. So the function is continuous on the intervals negative infinity to 5, and then it's continuous again between 5 and 8. Oops, 5 and 8. And then it's continuous again on the other side of 8 all the way to infinity. Alright, so basically everywhere except these 2 points. Alright, 15 is very similar. It's a radical function, and this thing is continuous everywhere across that domain. So everywhere we don't have a square root of a negative. So we take the 9x plus 1 that was under the radical, and we set that greater than or equal to 0 to find the domain. We get 9x is greater than or equal to negative 1, so x is greater than or equal to negative 1/9. And so the interval where this is continuous is from negative 1/9 to 0, negative 1/9 included. Alright, the next one, 16, is a little bit the same idea as 15, but because we have a square underneath this radical, we have to keep in mind that this thing could be positive in more than one place. So first of all, find the zeros. Find what makes x squared minus 6 equal to 0. Alright, and that happens when x equals plus or minus the square root of 6. So I'm going to make those my places where I break up the domain into 3 regions, 1, 2, 3. Now, as long as we get a positive output of this part, x squared minus 6, then we'll actually be able to graph this thing, right? And as long as we can graph it, it's continuous. So pick some numbers that are in each region. Alright, in this region, the square root of 6, if you think about it, the square root of 4 is 2, the square root of 9 is 3, so the square root of 6 is between 2 and 3. So if I pick something like negative 3, alright, and then in here if I pick 0, and then over here I'll pick positive 3. Alright, if I square negative 3, I get 9. 9 minus 6 is 3, so I get the square root of 3 here, which is positive. In here, 0, the 0 squared is 0, minus 6 is negative 6. So in here I get negative. This is underneath the radical. This is just this part. Okay? And then again here, if I square 3, I get 9. 9 minus 6 is 3. So I get a positive. Okay? I can take the square root of a positive, but I can't take the square root of a negative. So this is the domain, this is the domain, this is not part of the domain. So everything that's in the domain is where this is continuous. So from negative infinity to the negative square root of 6 is part of where it's continuous. And then it's not continuous. Oops, I guess I should include negative 6. And then it's not continuous in here, and then it is continuous again on the other side. So negative 6 to infinity. Alright, 17 wants us to find the limit, if it exists, of x goes to 4 of the square root of x minus 9. Alright, since plugging in 4 would give me a negative number here, 4 is not in the domain, so it kind of goes back to this last two problems. Since this is not in the domain, we're not getting a real number here. So in the set of real numbers, this limit does not exist. Alright, 18, basically the intermediate value theorem says if you have a function that's continuous, meaning if I draw it, I can't pick up my pen or my pencil. If that thing is continuous, then there exists a value in between the two endpoints of an interval. There exists some output that's in between the two outputs of the inputs of the interval. So to give you an example for this problem, we're looking at 2x to the fourth plus 10x cubed minus 6x minus 6. That's our function. So I'm going to come back to the main window. You can go under vars, come over to yvars, function. I've got it stored in y1, and then pick the two numbers. So they tell us to use -5. Alright, and then second enter gives you the last thing you just did back, and then -4. And notice that on one side of the interval at -5, the graph's up here in the positives, and on the other side of the interval, -4, the graph's down here in the negatives. Now, because this thing is continuous, that means I cannot lift my pen, and as I move left to right, I've got to make my way to that other dot. And so since I can't lift my pen because it's continuous, what the intermediate value theorem says is there has to be a 0 in there. Okay? So the way that we prove this, that there is a 0 in there, is we have to say that the function is continuous, and we know it is. Alright, we know it is because it's a polynomial, and all polynomials are continuous on their entire domain, and the domain is all real numbers for a polynomial. So f of x is continuous. Alright, f of -5, when I plugged in -5, I got a positive number. F of -4 was a negative number. Okay, and because that happened, we have a continuous function, a positive on one end of the interval, a negative on the other end. There has to be a 0 in there because the continuity, I have to go from above to below on a continuous function. So there's no way without lifting my pen that I can cross or cannot cross the x-axis. So that's what we're saying there, is because of the continuity of the function and the opposite or the sign change, there has to be a 0 somewhere in the interval. Alright, and then 19 and 20. I'm going to actually do 20 first because it's tougher than 19. Alright, 20 says f of x equals this piecewise function, x squared, if x is less than or equal to 2, and k times x if x is greater than 2. Alright, and it wants to find k to make this continuous. Alright, so what we basically need to do is plug in 2 into this function. Okay, and now we need to make k times 2 this boundary point where we're breaking it up. We're plugging that in for the x. We have to make that equal to the same output here. Alright, and then solve for k. So dividing by 2, we get k is equal to 2. Alright, so if the function is x squared and 2x for where we're breaking this thing up, then now this thing is continuous all across the domain. Okay, here's the point where we break it apart. So this is the possibility where we'd have a gap like we had on some of our previous slides, like this function. Alright, there's the potential for a gap there because we're breaking the domain up there. Okay, but because we just solve for k to make it 2, at this place where we break it up, we get 4 here, we also get 4 here. So we have continuity. That's what they're asking us to do here. Now, the reason why 19 is a little bit harder, obviously, is because you have an a and a b. So this time we have x squared, we have ax plus b, and then we have x plus 6. Alright, and then we're breaking it up here at -5. Here we're going to -2, and here we're above -2. Alright, so the way you do this is you plug in the -5 here, but you also plug in the -2 here, and you get two equations. So you get if I plug in -5 here, we know ax plus b has to equal what I get when I plug in -5 here. So -5a plus b has to equal 25 for this part to be continuous. It has to have the same output. But we also know that if I plug in -2, I have to get what I get when I plug in -2 here. So -2 plus 6. So I get -2a plus b equals 4 on the other one. Now what I have is a system of equations that has to be solved. So I'm going to just bring this underneath here. So I'm going to put a -2a plus b equals 4. I'm going to subtract this equation from this equation, so I'll lose a b. So I'm going to change all my signs here. Alright, and when I combine these, I get a -5a plus 2a is a positive 3a. The b's cancel with each other, and then 25 minus 4 is 21. Alright, so 3a equals 21, that means a equals 7. So that's one of the values, and then to find b, I can just plug it into either one of these things that are highlighted. So -2 times 7 plus b equals 4. -2 times 7 is -14 plus b equals 4. Oh, I'm sorry, this is a -3a, so that's a -7. I was thinking that wasn't working out. Alright, so that's a positive 14. So I subtract 14 over, and I get b equals -10. Alright, so that means that this middle equation would have to be -7x minus 10 for this to work out. Alright, so there's your solutions to this thing. Again, I'm going to post these as just a PDF, but you'll also have the video if you need it.